So I'm gonna try to push through the rest of tensor products and maybe get started on the other stuff today, see how that goes. Let me give you a corollary from what we talked about last time. Let's suppose that A prime, B prime are modules. Modules. And F made A prime, G, B prime are module homomorphisms. Then there's unique homomorphism between the tensor product the homomorphism H from the tensor product of A B, tensor product of A prime or B prime, such that H of A tensor B is F of A tensor G of B. So this is the math that's induced by this. This corollary follows pretty quickly from the statement of our universal property that the tensor product satisfies. Here is, in a certain sense, tensor product is intimately related to Hom in the following sense. So there's an analog, I should say. Theorem 12.8.5. Unlike Hom, the variable doesn't matter. Remember how if Hom varied in the first coordinate, then it was contravariant. If it varied the second coordinate, it's covariant. Well, tensor one side, tensor the other, they're isomorphic, at least for our purposes, comedic brains. So theorem 12.85. Let D, and R mod. Then is right exact. And I will make precise what I mean by that. That is, if A to B to C to 0, else F and G is exact, then so is a tensor D to B tensor D to C tensor D 0. And this is F tensor identity D, G tensor identity D. And I forgot to write this here. When I say F tensor the identity D, what that does is that takes the tensor. If I give you the tensor AD, this goes to F of A tensor D. So it does the identity in the second coordinate, and this one takes B tensor D to G of B tensor D. Yes.
So that you say tensor D is right exact, but like you mean it's a right exact functor?
That's what it is. Yeah. So that's what's meant by that. So in other words, tensor product, Hom tends to do good with the one-to-one stuff. Tensor product does good with the onto stuff. We say actually that the module D is flat if total exactness is. You're not guaranteed this. If this is one-to-one, if F is one-to-one, there's no guarantee this is one-to-one. And a module that makes one-to-ones here, one-to-one down here are called flat modules. I'm going to skip over that section, but if you're intrigued, there's just a short word about them in the notes that you can certainly ask me about if you're curious. I give a proof of this in the notes, but let me I'll just want to point out that as is usual, the difficult part of the proof is showing that the kernel of this is contained in the image of this. The onto-ness is not too bad because since G is onto, then for all B in, I'm sorry, for all C in C, the tensor C tensor D is in image of G tensor 1D. Right, because an arbitrary C here can be reached by some appropriate B here. So I can get any tensor CD. And since C tensor D is generated by these tensors, we are done. Because in particular, the image of G tensor 1 is a generating set for that tensor product. Also, the fact that the composition 2 in a row is 0, that is the image of this contained in the kernel of this, is not bad either. There's a proof that the other containment works, but I kind of want to go quickly through here. So if you are curious about that, again, just let me know.
What is right exact again? Or is it like that the tensor is on the right, like tensor is on the right?
No. It's the rightness of this. Notice how we end up, it's exact on the right side, but you don't have the 0 going in.
Okay, and then it's left if it was 0.
Yeah, so oftentimes they say that Hom is left exact. Because at the end game of Hom, there was always the 0, but maybe no 0 off.
Okay, but so this one you can't like switch it, like make it like the code.
Well, you can. I could do D tensor C and they're isomorphic. So that's why I only listed one thing. Yeah, Hom is different, in the different variables, but tensor product here is C tensor D and D tensor C are isomorphic. Yes.
Is there a D such that if you give it like a short exact sequence, you'll get a short exact sequence?
Those D's are called flat.
Okay, those are the flat.
Right. And in particular, if you have any, and yeah, so the flat modules are precisely the ones that preserve short exact sequences. And there's actually, we're not going to get into this unless you want to come talk to me again, but free modules are projective and projective modules are all flat, right? But there are flats that are not projective. I will give you an example. If you have any torsion-free module over a principal ideal domain, it's always flat. So for example, Q as a Z module is torsion-free. There's no elements of finite order other than the identity. But it's not projective. We actually showed that in the homework earlier. So that's an example, flat module that's not projective. Okay, as you might guess, because this was true for Hom as well, there's no worries when you have split sections. That splitting does lots of good work for you. So. Theorem 12.86. Theorem 12.86. Yeah. That's close. Right, so split exact works well for you. Now I'm gonna finish this up with, we did that last corollary, did this out of order. I'm gonna finish this up with a couple of kind of, big results here. Which I might actually, maybe I'll sort of give you magic literature on how to prove these. There. Whatever, I remember this. 12, 8, 9. This is called adjoint associativity. R is a commutative ring with one A, B, and C are R modules. A, B, and C are R modules. Then this is kind of a strange relationship between homomorphisms. I'm going to see if I can put together a homework problem that will exercise your brains on that without activating too much of the suicide hotline. So I'll try to design it carefully if I can do it. Then the homomorphisms from A tensor B to C is isomorphism is isomorphic to the homomorphisms from A to the homomorphisms B to C. Right? So I'm not going to prove this because I think I'm going to kind of develop something for you all, but just to kind of get us warmed up here, and because I myself think this is a little bit of fun, how would you even do such? So let's call this F. I want to construct some F. And the homomorphisms, A tensor. The hardest part in this, in showing this thing, is sitting there trying to wrap your head around what the heck is going on. Now, so I guess what we need to do is we need to start with a homomorphism from here to here. So suppose that F goes from A tensor B to C. And somehow we have to do some yin yang for this and get a homomorphism from A to homomorphisms from B to C. Right? Any ideas on how we might tackle such an animal? Actually, let me call this B, so it will distinguish my F here. That might be a little bit easier. F of phi, this should now be a homomorphism from A, the homomorphisms of B, C, right? That's what this should be. Yeah, it is on how to do it. So F of this should take an input from A, right? So F of phi, this is F of phi over here. This should be a homomorphism from A. So it should take an input from A. And its output should be, this should now be a homomorphism from B to C, right? So this should take an input and give an output of C, right? Everybody kind of follow this mess? So start with phi, it goes from A tensor B to C. F of phi is now a homomorphism that takes input from A and barks out a homomorphism from B to C. So at this point here, this should be a homomorphism from B to C, right? You took an input from A and it gives this. So this takes an input from B and it gives an output of C. Can anybody guess what that output might be?
Is it B of A tensor B?
Whoops. Very good. That's the way this works. Your input is F phi. It is a homomorphism by homomorphism B to C, and this is how it works, right? Because notice the output is actually C. See if you can figure out how to work it backwards, right? Because if you were to sit down and prove it, the fact that this is, once you write these maps down, the fact that they're homomorphisms, not too bad, because everything, all the players are homomorphisms, right? So it's not too bad. The difficult thing is showing that this stupid thing is one to one and onto, right? And that's why I say, see if you could go back, because the easiest way to do that is to find out the function. So F goes this way. See if you can find the natural function G that goes back, and then show that the composition gives you the identity. Right? Show each composition. Do F and G, do G and F, they both give the appropriate identity function. That's the best way to go about that.
He's going. B takes in only A.
Well,
Does B only take in A, or it takes in A?
no, actually, phi is a homomorphism that goes from A tensor B to C. And so it's defined on tensors, but actually, phi is actually defined on sums of tensors, because a typical element of this is a sum of tensors. But if I tell you what it does to the tensor, I've told you everything you need to know, because these are R modular homomorphisms. So when I tell you what they do to generators, I've told you what it does to everything, right? Okay, other questions?
The tensor product of A and B, big A and big B, is generated by the little tensors?
It's generated by it, that's right.
Okay.
So everything in home A tensor B is a sum of tensors, finite sum of tensors, A sub I tensor B sub I.
We had something similar in ring theory where we had the product of two ideals is the sum of everything just to force it to be an ideal.
That's right.
Okay.
That's what you're doing. You're forcing it to be closed under addition. And that's what you're doing here, because what you have, if you add two tensors, these are technically cosets.
Sure.
There's no, this is a particular type of coset. When you add these two things up, there's no guarantee it's still a coset of that form, right? So that's the problem.
Is A tensor B, these are little, the same as RA tensor one over RB? Assuming you have a division. Or,
So are you asking this?
yes,
If you can divide by R, yes. Okay. Here's the final bit before we talk about modules over a PID. There, 12, 8, 10. I'd like you to think about how to prove this too. This is another question. Let A, AI, B, BI, be R modules. Then A tensor, the direct sum of BI is isomorphic to the direct sum A tensor BI. And this follows from other stuff, but I'm gonna write it out for completeness. If you look at the direct sum, J and J of AJ tensor B, this is isomorphic to the direct sum, J and J of AJ tensor. So this is what we talked about last time, that tensor product commutes with direct sum. So it distributes exactly the way you want. And this is even for as big of an index set as you want. But at the end of the day, if you want to just be pedestrian and do some computations with it, tensor product is really just of these modules. It's just generated by these tensors under those rules that we have for collapse, right? I mean, if you have the same thing in the first coordinate, you can sort of collapse down and so. Okay. Any questions? Okay, so this is okay, so I gave you on the homework this last time, I gave you a couple of what I would consider to be sort of helpful warm-up problems about linear algebra. I think I asked you things about similar matrices and this business about it's diagonalizable if and only if it's got a basis consisting of eigenvectors. We can go over that if your linear algebra was way in the past or whatever it happens to be. How many of you have ever seen canonical forms? Any computer? I think sometimes computer people dig these things. So canonical forms of matrices are, let me give you an example. So let me do this here. Well, this matrix is not so bad, right? I'd like to do computation because it's up angle. What's its determinant?
Negative
-10, right? Remember upper triangular or lower triangular is fine, diagonal elements. This is actually, let me show you an easier matrix. That's a diagonal matrix, right? These two matrices are similar. And also, I could muck around with this and make this a pretty complicated matrix to do this. Would everybody agree that this is the easiest matrix to work with? If you're doing some kind of computations, this kind of thing. I mean, only a scalar matrix is easier than this, right? I mean, diagonal matrices are great. They're not the center of the matrix group, but they're as good as it gets pretty much, right? The difference between, and of course, I could do some kind of scramble with this. I could conjugate this a couple of times and get some matrix like this that's full of all kinds of crazy crap, right? But this one is the easiest one. What would the difference between these matrices be if all three of these are conjugate? It's just how you chose your basis, right? So some complicated random matrix might be a mess, can be written in a much easier form if you pick your basis carefully, right? Now, doing a change of basis to make your matrix more convenient is sometimes extremely useful. And in fact, when you conjugate a matrix, and you can actually conjugate if I have a conjugate of this that's full of all kinds of crazy stuff, conjugating back as this just, everything's preserved. Not everything, but the eigenvalues are preserved and under this, and there's lots of important things in the linear transformation that are preserved. So canonical forms are very important. Let me give you another example here. Here's an example that you probably won't see in a linear algebra class. Let's look at, we'll look at GL. No. Let's look at this group. This is kind of a Ruby group. So this is the set of all 3x3 matrices over F2 that are invertible. Right? By the way, how many of these are there? No. There's 168 of these. Anybody know how to figure that out? Let's think of this building, this just in 3 rows. I'm going to build an arbitrary matrix and GL 3 2. Let's take it one row at a time. Now I've got to make sure as I progress that this matrix is invertible. So how many choices do I have for row 1? just in the blind, how many choices do I have to fill out? So the first row will have three entries. All of them from the field of two elements, right? Either one or zero. How many ways do I have to just fill that up? Eight. Everybody agree with that? Two choices for each. Got eight. But there's one choice I can't use.
0.
I can't use zeros across the board because then the determinant is zero and I'm dead in the water. Right?
Wait, why do you only have 8 choices?
Well, because you've got three entries. And you've got two choices for each because it's either zero bar or one bar.
Oh,
Right, so it's two
okay.
cubed. But I'm gonna take one away. Because I can't have the row consisting of all zeros, right? How many ways are there to build the second row? Now I've gotta be careful because I've chosen the first row. And I still don't want the determinant to be zero. So how do I avoid that?
Six choices.
Yeah, that's right. How'd you get that?
Like you can't select the previous row, you can't select 0.
Okay. Well, right. So let me put that in more compact form here. What you select here is all 8 choices, but you can't have any multiple of this row. So you can't have 0 times this row or 1 times this row. So it's 8 minus 2. Right. Going with that pattern, how many choices do you have right here? Yeah, that's right. So you've got 8 choices in the blind, but you can't have any linear combination of these rows, right? Because I've got to keep the rows linearly independent. So I've got to, and how many linear combinations are there of these rows? 2 times 2, 4. So this is 7, 6, 4. I get 168. Yes.
I just was wondering what exactly you mean by conjugate?
That's a conjugate.
So it's conjugate. Oh, sure. Yeah.
Right. And more generally with matrices, we don't demand, I don't demand that the matrix be invertible, but I do demand that the G be invertible.
Right.
Okay. Like that. Everybody okay with that?
How is that? Why can't we?
Oh, the last one? 8 choices, but I can't have a linear combination of either of these first two rows that I've selected. And the number of linear combinations, you can multiply this by 0, 1, this by 0, 1. So there's 4 linear combinations of these. By the way, if I'm not mistaken, and I should check myself on this, I believe that this is if you look at non-abelian simple groups, this one's the second smallest. Right? A5 is the smallest, and I believe it's the second. Y'all remember the class equation? Right, it broke up a group into its conjugates and classes. How many matrices are there of order 7? In GL2, GL3, F2 are of order 7. Well, I'll use the CELO theorems here. 168. That looks like 2 cubed times 3 times 7. Right. So the number of CELO 7 groups are, well, let's see. N is equivalent to 1 mod 7. And N divides what it is. It's not 7, which is 24. So how many are there? There have to be eight. Well, I guess there could be one, right? But this, you could take it as given that this is a simple group. So if it's a simple, so your only choices here, the only numbers equivalent to 1 mod 7 that divide 21, let's see, we're 1, 8, 15, 22. Okay, the only ones are 1 and 8. But if the group is simple, which this one is, it can't be 1 because then that CLO 7 group would be normal, right? So it has to have 8. So how many elements of order 7 are there? That sounds right. So each CLO 7 group has 7 elements, but one of them's the identity, so you can chuck it. So each CLO 7 group has 6 elements of order 7, and there's 8 of them. There's a 6 times 8, which is 48 elements of order 7. That's a lot, right? There's 48 of them. I don't want to pick through 48 freaking matrices. How many conjugacy classes are there? Right? It's all we, that would be of interest, just fun conjugacy classes. Well, if n is of order 7, then the conjugacy class of this is P inverse NP, conjugacy class of M, as P is in GL3 F2. This is just a set of all conjugates, right? If I could conjugate any matrix down to a canonical form, a standard form, this would make my life much easier. So this is kind of my other kind of push for the canonical form. Computations with respect to good bases, and even an old-fashioned group theory problem can be done with some as an application to what we're going to do now. And I'm going to start, and I'm not going to go through a lot of the details here. Again, here's my goal for this section. It's chapter 13 in your notes, modules over PID in the canonical form. I am not going to get as much in the weeds as I do with a graduate class. I'm going to tell you about some of this stuff, and I'm going to show you how to compute this stuff. I mean, like if you're stuck on a desert island and you're dying of thirst and you need to compute a conjugacy class for one last time before you go, I want you to have that power. And so I'm going to give you some stuff that shows you how to compute this. So I'm going to start with the structure of a finitely generated R module over a PID. And again, I'm not going to go, there's a couple things I want to prove because I think they're interesting, but I'm going to gloss over some of it because for the most part, most of you have seen this, even though you haven't seen it in this generality. You've basically seen all you need to when you looked at how many, do you all recall when you did the fundamental theorem of finitely generated abelian groups, and you could decompose them into, if you hadn't seen it, I'm going to show you that anyway, so don't worry. So let's start this off with in the following fashion. Yes. Theorem 13.1.1. Here I'm going to let I'm going to start off here. Let A be an R module. All my arrays will be created with 1. Let R be an integral domain, A an R module, and A an element of Oh, and one more definition. And so I'm gonna have that kind of script D of A. This is the set of, for my fixed A here, D of A is the set of everything and R that kills A. A. Um, So the set of everything that kills some fixed A is an ideal. B, A sub T. This is the set of A and A, such that TA is equal to, is non-zero. Is a submodule. So let me point out that, of course, one thing that is always in DA, no matter what A is zero, right? But some naughty A's might have non-zero things that kill them. AT, this is sometimes called the torsion element, or torsion elements of the module. These are everything in A, such that D of A is not zero. Translation, everything in A that is killed by something that is not zero, right? If it's killed by something that's not zero, then it lives in A sub T. And this is a submodule of A. By the way, for B, you definitely need R as an interval domain. Of course, this is an ideal. R mod D of A is isomorphic to the ideal generated by A and R. And let me up the voltage here. Now let's suppose also that R is a PID. If R is a PID and P is a prime, then if PIA equals zero, that is, the ideal P to the I power generated by P to the I is contained in dA. Then this is actually generated by a prime power. J is less than or
Dr. Clayton,
by.
when you were writing on the left-hand side, C, is that R localized at A or R?
No, it's RA.
Okay.
It's just the ideal in R generated by A. And if dA is equal to PI, then PJ A is not zero for all J less than I. Okay, so let's kind of go through the proof of this. A good chunk of this, I think, is pretty routine. Proof. Part A. Okay, why is this true? Well, first of all, this is a non-empty set, right? Because zero is in here for sure, right? So let X, Y. Let's call it Y. Being DA. And R, then X plus RY times A is, XA plus RYA, which is 0. Therefore, X plus RY is in DA. So it's an ideal. Right. That's the ideal condition. Number 2. Show that, this collection, AT is a submodel. So B, let me start off this way. AT is not the empty set. Maybe this is a little, there's probably just a little bit more that needs to be said here. Can somebody tell me why AT is not the empty set? Can somebody tell me something for sure that has to be an AT? 0. Okay, but now we need to, yes, it better be if it's a submodule, better contain 0. What's something that's in D0 that's not 0? There's only one thing other than 0 that I guaranteed you was in this ring. What? 1, right? 1 times, since this is a ring with 1 times 0 is 0, and so this is not empty as 0 is in 8. But we're still going to need domain here. So suppose X and Y are in AT. This means there exists such that Rx equals 0 and SY equals 0. Everybody agree with that? That's what it means for X and Y being AT. There's something other than 0 that kills them. Right, so here are my non-zero R and S that kill this. Can anybody think of something that kills XY?
RS.
Not XY, X plus Y. That's right. Right, because the R part kills X and the ring's commutative and the S part kills Y. But there's one important detail that we should not gloss over here. Anybody know what it is? So we produced an element. Everybody agree we produced an element RS that kills X minus Y. And so I'm going to use that. I want to use that to claim, okay, X minus Y is in AT. What do I have to assure myself of for X minus Y to be in AT? I need RS to be what? Non-zero. That's right. Since R is a domain and RS are not 0, this implies RS is not 0. So X minus Y is in AT. Right. Also note if alpha is in R, then R alpha X equals alpha RX equals 0. So alpha X is in AT as well. So in fact, it is a submodule. Right. Any questions on that? I'll do this. Maybe we'll talk about the PID crap next time. This one I can pound out in blink of an eye. Consider phi from R to RA. Given by phi of R equals RA. Is everybody with me on the fact that this is an R module homomorphism, right? Everybody cool with that? Would you also agree that it's onto, right? Because anything over here is of this form, and it would just come from R, right? Okay, so far. The kernel of phi is the set of R in R, such that RA equals 0, which is precisely that thing. So by the first isomorphism theorem, R mod this is isomorphic by RA. And there you go. Gotta love that first isomorphism theorem. Okay. Any questions? Any questions? All right. Well, we will catch you all on Friday.